in problem 7.45, we have a block that slides down an incline and then travels around a loop-to-loop track. And the question is, how high must this block be in order to make it around this loop? Now, the loop has a radius of r. So the height of a mast that's at the top of this loop right here, that's got to be 2r. And we're going to assume that using this as the lowest point, that there's a height h, such that it'll make it around this loop. Now, we need to look at, if it's not going fast enough, it's not going to make it around this track. It's going to fall. So we need to analyze a little bit what happens when it goes around this loop here. At the top, there will be a force of the track, and there will be the force of gravity that's pulling this thing down. And at the top, it'll be traveling with a velocity v. And if it's not going fast enough, of course, it'll fall. Actually, what turns out is this will occur whenever ft is 0. If we, and here's the mass m right here, okay? All right, so let's go ahead and look at what's given here. We'll look at that first. Is the radius of the loop. And the radius of the loop, okay? What we're looking for is the height, such it'll make it around that loop. Now, we can get a relationship between the height here and the velocity that this thing is traveling using the conservation of energy. So we're going to use that first. We're going to call this the starting position and evaluate the energy there. And here is going to be where it finishes right here. So we can compare the energy at those two locations and get an idea based on the kinetic energy it has here, how fast it's going. So the theory would be that the kinetic energy that it finishes with here plus the potential energy that it has there must be equal to the potential energy that it starts with, and that's all the energy it has up there. It's not moving. In order to be able to make it around the track, the force of the track plus the force of gravity must produce a centripetal force to keep it on the track. Now, this centripetal force will be a minimum whenever the force of the track is equal to 0. That's the point at which it'll fall, okay? If the velocity is any less than the velocity required to keep it in contact, and the force of gravity is what provides that centripetal force. So let's go ahead and put in our theory that we're assuming that Ft equals 0 at the point that it would leave the track. Well, let's go ahead then, and let's go ahead and use the conservation of energy then. First, and put in the values for the energy it has at the beginning and the end of the process. Okay, it's going to have kinetic energy. Kinetic energy finished. That's going to be 1/2 mv squared. It's going to have potential energy, which is m G times its height, and its height up there is 2r. At the top is 2r. That's got to be equal to the centripetal, equal to the potential energy that it started with, and that's mgh. Okay, we can look at this relationship right here to give us an idea of how the velocity is related to the radius, because right here you can see mg. Here's mg equals mv square over r. So we could solve for v square here, and we can see that v square equals g times r, and that we can put into our conservation of energy equation. So give me a little bit more room. I'm going to get this out of the way here. And if I do that, put the, oh, by the way, notice here, we could go ahead and get rid of all these m's right here. That'd help us quite a bit right there. So I'm going to put this v square equals gr in there for v square. So I would have 1/2 g times r. Okay, that equals 2gr, plus 2gr. That's this term right here. And then that's got to equal to g times h. And now we can get rid of the g's. And you can solve this right here, and you can see that h equals 2.5 r, like that. Okay, so any height equal to that or greater would keep this object moving around the track so it wouldn't fall off at the top.